So good afternoon everyone. We're done discussing the maximization problem using graphical method. So today I'll be discussing the minimization problem again using the graphical method. So this is an example of that. Hank wants to mix up 500 pounds of special dog food supplement. So there are two principal ingredients in the mixture, both sources of protein, P1 and P2. P1 costs 500 a pound and P2 costs 800 a pound. Chemical dictates that the constraint that a mixture contain not more than 400 pounds of P1 and at least 200 pounds of P2. So you have to formulate an LP model and solve the best combination that has the least cost. So the same thing as what we did in the maximization problem, we're going to assume the variables unknown. So for this example, we are looking for the amount of P1 and P2 to be mixed. That's why we're going to assume X1 be the amount of P1 to be mixed and X2 be the amount of P2 to be mixed. And instead of total profit, we will be solving the total cost. So if we write down the given in the table, we'll be able to see that we have three constraints. So for the first constraint, as mentioned in the problem, the mixture is equal to 500 pounds. So meaning your P1 and also your P2, it is equal to 500 pounds. For constraint number 2, again, as mentioned, the mixture should not be more than 400 pounds of P1. That's why for your constraint number 2, it is your P1 is less than or equal to 400. And the last one is at least 200 pounds of P2, the total mixture. So your constraint number 3 will be P2 is greater than or equal to 200 pounds. And the total cost is 500 per pound for P1 and 800 per pound for P2. So, if we're going to write down the LP model or formulate the LP model, this will become your objective function. So, instead of maximization, you're going to minimize now the total cost, which is equal to 500 x1 plus 800 x2. Subject to the three constraints mentioned. So x1 plus x2 is equal to 500. Your second constraint is x1 is less than or equal to 400. And the third constraint is x2 is greater than or equal to 200. Do not forget also to write down the non-negativity constraint, which is x1 and x2 should be greater than or equal to 0. Because you cannot mix a negative x1 and x2. So there is no such thing. Okay, now, we're going to plot the constraint. For the first equation, again, the same thing as what we did in maximization. We're going to assume one variable is equal to 0. So for the first equation, x1 plus x2 is equal to 500. If x1 is equal to 0, your x2 will be 500. And if x2 is equal to 0, your x1 is 500. So if we're going to plot it in the Cartesian plane, your x1 is equal to 500 and your x2 is equal to 500. So you're just going to connect the 2 points. You have to remember in maximization, diba? When we shade the feasible area, the example that I gave is only greater than or equal to. So if it is greater than or equal to, if this is the line, the feasible area will be above or away from the 0, 0 value of x and y. If it is less than or equal to, it should be below the line or going to the 0, 0 x and y value. And if the sign that you have is equal, so it's not on the right or left side or upper and lower, but rather on the line itself. So meaning the value that you should be getting is within this line only. Okay? So, for the second equation, we have your x1 should be less than or equal to 400. So, we do know that the value of x2 is 0 right away and x1 is 400. So, if we're going to plot it, your x1 is 400 and it's less than or equal to, so the feasible area is this, going to the 0 value of x and y. So this is the feasible area, less than or equal to. The same manner with the third equation, x2 is greater than or equal to 200. So we do know that the value of x1 is already 0 and your x2 is 200. So if we're going to plot it, your x2 is 200, I mean. So this vertical line is your third constraint. Okay? Sabi, it is greater than or equal to. So meaning, if it is greater than or equal to, your feasible area is away from the 0 value of your x and y. So this will be your feasible area for constraint number 3. We have to remember again that we should meet all the constraints. Meaning, if we're going to consider the corner points, only those points na na-meet yung 3 constraints mentioned. Okay? So, we have a lot of corner points here that we need to analyze whether it will be included. This one, this, and this. And also this one. So, let's start with this one. Are we going to consider this? Yes, it passes through constraint number 1, but unfortunately, it doesn't. It's outside the feasible area of x2 and also x3. So we don't consider this point. How about this? It's okay with x2, but it's not okay with x3 and x1. So we don't consider this one. How about this point? It's okay with x1 and okay with x2, but not okay with x3. Kasi ito yung feasible area ng x3. How about this? Okay with x2 and x3, but not with x1. So we don't consider it. How about this point? So it passes through the first constraint. So nasa feasible area ng x2 and also it is equal to the feasible area of x3. So we name it as point A. How about this one? Okay with x3, okay with x2, but it doesn't passes through to the first constraint, so we don't consider it. How about this one? So it passes sa line ng x1, sa x3 it's within the feasible area, and sa x2 it's within the feasible area. So we will be considering only A and B. So these corner points, dito natin makikita yung the most optimal solution. Okay? So at A, we start with B because B, x2 is equal to 500, given na. Okay? So if x2 is equal to 500, we substitute it with the total cost. The total cost is equal to 400,000. So at A, we do know that the value of your x2 is 200. And from the first equation that we have, your x1 plus x2 should be equal to 500. So, meaning you'll be able to know that your x1 is equal to 300. So, if we substitute it with the total cost formula that we have, the total cost is 310,000. So, if we compare the two, we do know that the least cost will be in point A. So what will be your decision now? Your decision is to produce 300 pounds of P1 and 200 pounds of P2 to get a minimum cost of 310,000. That ends the minimization lecture. Thank you.